Now let's turn our attention to AWK, which is a field processor, which stands in stark contrast to grep, which is a line processor. They're often used in conjunction, however, to achieve tasks surrounding the parsing of data. So we'll label this section AWK, and it features a field processor that's again as old as Linux, certainly, and perhaps as old as Unix. Standard tool. Now we should just note that it also supports, like grep, regular expressions, or grep-style POSIX regular expressions. There are two major types of regular expressions in the wild, POSIX and Perl. There are others, but most tools have conformed to Perl and or POSIX. So AWK supports POSIX style or grep style regular expressions. So how do we use AWK? What's so important about it? Now we'll continue to focus on our data set because it's simple, and then once we've completed our studies of our data set, we'll look at real data such as the system log files. So let's take a look at what's happening here. So in our document, we've got a number of lines. According to gedit, we have 13 lines. And these 13 lines contain a number of fields. Some of them 1, others 3, some 4 because of the spaces. Insofar as AWK is concerned, the default delimiter is space or white space. So when it parses by default, it is using white space to extract the fields. So 3, default field delimiter is white space. And this can be influenced, which means if you're parsing documents that have a different delimiter such as comma or semicolon or some other type of character, you can instruct AWK on the command line to use that other delimiter. So that's not an issue, but it defaults to space, which you should be wary or clear of. Which means you'll look at this particular document, wherever you see a space followed by, let's say, another space or printable characters, AWK will construe that to mean a field, which means as it processes lines, as it loops through these lines, it stores the fields or the columns into tokens. And those tokens can be extracted during your usage of AWK. So let's just note that it stores fields or columns into tokens, which then become accessible during processing, meaning during the operation of AWK. Which means as AWK reads this particular file, grep.test.txt, it reads each line individually, so 1 through 13, and per line it stores the fields based on a whitespace separator into those tokens that we've mentioned. So for line number 1, there will only be 1 column or 1 token or 1 field. For line number 2, there will be 3 columns or 3 tokens or 3 fields. Line number 3, 2 columns or 2 tokens or 2 fields, and so on. For example, this line, which contains an L followed by a white space, would constitute 2 tokens. L would be the first field, and AWK CBT would be the second field, or token, or column. So that's how AWK operates. It loops over input 1 line at a time. Let's just note that as well. So loops over input 1 line at a time. And it tokenizes the columns or fields as it encounters them and makes them available. So let's look at parsing this document to see what's of interest to us. So you can use AWK directly against a text file, or you can send output to AWK using grep. We'll do both. Let's begin initially, as we would with any application or any program, by processing the input directly, as opposed to using a pipe, which is an indirect means of processing information. So to process grep.test.text, we'll use awk against it, grep.test.text. But we need to tell awk what to do. And that's what comes between awk, the name of the process, and the input file. So the general syntax is awk instructions file, or awk instructions, and then awk waits on standard in for you to supply input. Let's just note that as well. We'll accept input from file or stdin or pipe. So you can pipe to it, you can input using your keyboard, or you can send information via file. So what do we want to tell awk to do? Well, you can tell awk to do a number of things. You can tell it to print the contents of the full line as encountered, for example. That doesn't do much for us. That's exactly how cat would work. But it's important to know that awk can do it. It will read a file and print the entire line. When we parse, we instruct it right after awk, and for example, in between single quotes, in between curly braces, we specify the instructions. And the instructions normally surround a print statement, such as print 0. Print 0 tells awk to print the entire line that was processed. Now, awk still tokenizes the items on the lines, but it will represent those tokens as the complete or entire line when instructed to do so via print 0. So let's see what happens when we try this from the shell. And by the way, which awk tells us it's in bin, and an RPM query file, bin awk, will tell us that it belongs to the gawk RPM. So let's execute awk, and with the print 0 statement, notice it simply printed the contents of the file. If we pipe the output into WC-L, you'll see that it's indeed 13 lines. So print 0 does nothing magical or anything different than what cat would do. Let's cat grep.test.text, and it does the same thing, piping the output into WC-L, 13 lines. So print 0 prints the entire line. Let's just note that. Prints the entire line, or prints each line. So prints each line in its entirety. And that's fine. But the power of awk is realized when you print specific columns. Now let's look at our data set. Supposing we wanted to re-represent or extract column number 1 from each of the lines. Then, using awk and in between curly braces, we'll instruct it to print column number 1 or token number 1 or field number 1 from grep.test.text. So prints column number 1 from each line. Which of course begs the question, what if a line contains white space in its first column? So we'll test that momentarily. So there's awk printing all 13 lines, but only the first column from those 13 lines. And these are those items. And of course we can cross-reference this. Let's just close this extra shell in our gedit window. So indeed. Now back to that question. What if a line begins with white space but has a second column? What does that mean from the perspective of awk? So we've got a space followed by Linux CBT. So space starts the line. Let's see how awk interprets this output. Notice it treats the string Linux CBT printing or printable string as the first column. So the white space is simply ignored, and what follows the white space is treated as a first field, even if we add a second white space. So now we've got 2 white spaces. So in that case, this is still treated as the first column. But subsequent to the first column, if you include a space and then a printable character, then the first printable character will be treated as the second column, or unless you use a different delimiter. Now what if we wanted to print, let's say, a different column, such as column number 2? Not all lines contain 2 columns, but it's still quite possible. Wherever a line does not contain two columns, awk will simply not print it. So let's print 2. And there you see, these are the lines that contain printable strings in column number 2. The other lines which are printed are spaces. In other words, they're empty at column number 2. So for the first one, for example, Linux, after the X character in the word Linux, there is no second column. So that renders an empty line. Now for the next one, red space hat. Well, hat is the second column, so it printed. 2011 should come after hat because that line contains 2011. Then after 2011 is the line Linux CBT, which contains nothing after Linux CBT. So in each case where a line doesn't contain a matching column, an empty line is printed, which can be suppressed, but that is a default behavior, to print an empty line where items do not exist. So that's how that works. Now you can combine the columns that you print using the various tokens that are of interest. So for example, let's just include what we've just printed using awk print2 grep.test.text prints column number 2 from each line. And as mentioned, you can alter the order. So supposing we wanted to reorder the output such that column 2 comes first, followed by column 1. So we could print 2, comma 1, and this would print column number 2 first, which for production data sets may be the thing that you need. So prints column 1 followed by or then column number 2. So let's copy and paste this and try this out again. Sometimes you need to reorder data, such as data that may have come from a spreadsheet or database originally and made its way to a text file. awk is the tool that will help you to reorder things. Now, of course, the output looks jumbled, but indeed it's reversed. For example, look at the line that contains hat space red. It was originally red space hat, so now it's hat space red, so you can reorder it. And you can also intersperse characters. So, for example, in between we could print a new character. You can even change the output delimiter. So you could say, for example, put a space between them and print it that way. That puts an additional space, or perhaps some sort of marker like a hyphen to indicate the differences between the columns. So you can change things. You can include non-printing characters such as tab and other white space characters and so on. So you can reorder things at will by indicating the columns that are of interest. And of course you can transform the data using different output delimiters if you need to, for example. So you can print the entire line, you can print specific characters, and also, as we've mentioned, there's the ability to search using regular expressions, which is one important portion of using awk. So for example, we've been simply taking the input and printing the tokenized columns as output, such as columns 1 and 2. But what if we wanted to search specific lines as we can with grep and then perform the output transformations, meaning the printing of the columns that are of interest to us? Well, what does that mean? Well, supposing we're not interested in all of these lines. We just want specific lines and then specific columns from those lines. That's what we mean. awk has an alternate syntax, which is as follows. awk followed by in between 2 forward slashes, which is the way you specify regular expressions with most tools, Perl included. And in between these forward slashes, we can specify the regex, such as the word red. This will search for red in the input and then follow the instructions between curly braces, such as print column 1 or print the whole line. For example, let's print the whole line wherever it's found. And that's going to be from grep.test.text. So this prints all columns where line includes the word red. And let's try this out and see how it performs. This gives us grep-like capability within awk, which obviates the need to use grep for these types of searches. So in this case, only the line that contains red was parsed and then processed, which now means we can extract even more interesting columns, such as show me column number 1 or show me token number 3. Or how about reordering the content using a different delimiter? So let's print the original order, 1 followed by, let's put a hyphen, 2, notice the variables are not protected by quotes, followed by hyphen, followed by variable 3. And notice it's transformed the text quite simply using our new delimiter, hyphen. And there are other ways to do this, of course. This is just one way. Again, AWK's much more complex than this. We spend a whole product actually covering AWK, Linux CBT AWK Set Edition. Is worth having a look in the event that you want to learn much more about AWK. Let's just note that this prints all columns with transformations where line includes red. And this, of course, begs the question concerning case insensitivity. So supposing we include the following. This is now all lowercase, but our search, of course, is premised on uppercase. Notice that only one line, and one line only, is still of interest. So that means if you need to perform some sort of case-insensitive search, you will have to make a transformation to make that happen. Another thing you can do is search for matches in particular portions of the string to then make decisions on. For example, let's take a look at grep test text. Supposing we wanted to transform or print output based on the match on a specific field, such as where field number 2 is equal to 2011, then extract those records. So that's another or a conditional way in which you may execute AWK. So for example, AWK, and everything's between the single quotes and curly braces, so let's include them. And what we'll note here is if a particular column, so let's see which column's of interest to us, and these are the tokens that are matched. So if column number 2 is equal to 2011, so column 2, and this is going to be a tilde regular expressions reference between forward slash is equal to 2011, then do some sort of action, such as print all of the records. Perhaps print a particular column or series of columns. So let's print all records, for example, see what happens here. So let's just note that this will print all columns of records containing the string 2011 in the second column, which adds even more power than grep, because as mentioned, grep does not parse fields, but rather simply entire lines. Let's try this out. And we didn't close with a curly brace. Nor did we close the regular expression search with the parentheses, so we clobbered the input, and this should be more like it. So if second column is regular expressions 2011, then perform print 0, and that's more like it. So now this prints all of the records containing 2011 in the second column. Let's look for content that does not contain 2011 in the second column, and there's no such thing. So what we should do is perhaps alter this to include 2011 in the first column. And then let's save the changes and update our notes. So the parentheses should be right outside of the regular expression search, and this should terminate with the curly brace. We hit the wrong character, and that does the trick. Now let's try the search again now that we've updated our content. And indeed, only items containing 2011 in the second column are returned. And if we update the search, where 2011 is in the first, then that particular record is returned. And of course, we could print specific items, such as show me column number 2, or perhaps reorder the columns, 2 comma, maybe some sort of separator that we intersperse, followed by column 1, for example. And let's just double check there is no column number 1 in this particular case. Let's just double check. That should be print 2, followed by hyphen, followed by comma, follow $1. So this output is thrown off. Let's cat the contents of grep test text, and the spacing is throwing it off. But nonetheless, we're able to perform the match based on a specific column, so it comes out as expected. Let's just try this again. It's the single quotes that's throwing us off. It's not actually the space. It should be the single quote, because we're wrapping the output in single quote, and that's more like it. So that works. It should be double quotes because we're wrapping the entire awk statement within single quotes. So now this reorders the output, searching, of course, where column 1 is equivalent to some sort of match. And you can match anything that you'd like. And you can also perform other types of regular expression matches that suit your needs. For example, let's take a look at our content to see what might be of interest to parse. So supposing we wanted all lines that terminate with 2011. Now we know that the $ symbol is the meta character, the anchor meta character, which handles the termination of content on lines. So in between curly braces, whenever executing awk, you specify a pattern followed by an action, and you lump everything between curly braces for the most part. So now we're looking for the line to end. We don't actually need an if statement. We could just search for the character that's of interest and then perform an action. So let's go ahead and just indicate between forward slashes or regular expression symbols what we're searching for. So we're searching for lines terminating with 2011. So we can do 2011 and the $ symbol, indicating that 2011 must end the line, and if so, print the entire line. So show me all those lines. And of course we need a file name. If we don't specify a file name, then it waits on standard in. And let's see what happens in this particular case. So now we're specifying the regular expression to the left, which is a pattern to match, and then the action when that pattern is matched. Now normally we don't specify a pattern, and that means to search the entire line and tokenize all of the columns. But when you specify a pattern, as we're doing here, then, or as we did earlier with the if statement, then you force the selection of particular records. So let's check our syntax. And notice this has extracted the 2 lines where 2011 ends the lines. And we can always grep to ensure that that's consistent with grep's view. So 2011 $ from grep.test.text, and the same 2 lines are returned. So grep is consistent with that particular view that awk holds. So this is one way to do it. And of course you can still tokenize. So show me number 1, for example, for those particular lines. Now a word about the other forms of input, since we've looked at grep and we've discussed standard in. So let's perform the same search, but this time omitting the file name. So waits on std in for input. In the most recent case, prints lines ending in 2011. Let's see what happens in this particular case. It's going to be awk, and if it ends whatever input supplied with 2011, it'll print. So notice it waits for us in standard in, and if we supply content, let's try 2010, nothing. 2011, it prints. 2012, 2020, 2099, 2199. How about 2111? It doesn't work. It has to end with 2011, and then it prints. And once you're finished with the input, indicate Control D to terminate, and then that returns you to the prompt, and the exit status is 0 because the searches were performed successfully. So that is one way to execute awk. Notice I've specified a hyphen in this case. Most utilities will understand hyphen in the place of a file name to mean standard in. Now awk supports a number of other features, including the ability to accept begin and end statements, to transform data, for example, using string transformations such as uppercase, lowercase, numerical computations, and otherwise. So it isn't limited to just these types of searches, but these are some of the common types of searches that you'll perform. Now let's look at piping. So awk, and let's search for the same string, 2011, terminating the line. And when we find it, let's print the entire line, for now at least. And let's just note, accepts a pipe. Now, this will wait on standard in by default, but if we pipe to it, then it will accept the contents of the pipe. So that means we need to send information to it. That means we could grep 2011, perhaps from var log messages, and then pipe the output into awk. But awk will only print if the line terminates with 2011, which we are not likely to see. But nonetheless, let's just show you how this would work. Now we're not able to read the file, so let's su in. And let's try it as root. And notice it ran, but it doesn't exist. Meaning there are no lines in var log messages that this would be able to extract, that end with, that is 2011, or tail with 2011. So we can also try that with grep. Let's su back in. And let's grep where the line terminates at 2011 from var log messages. And indeed, grep was unable to find it. So that's why awk was unable to print anything. But what if we were to grep from our file, grep.test.txt, where lines end with the string 2011? Let's try that out. And indeed it works. So grep extracted those two lines and then sent them to awk. And then of course, to prove it, let's just print the second column. And indeed, or the first column, or perhaps second followed by some sort of delimiter followed by the first. And indeed, and this is should be double quotes. We tend to always default to single quotes. And indeed, it prints it that way as well with the appropriate spacing between the two columns. So long as the string matches, you can send the information to awk via pipe or standard in or from a file, and it'll do its job accordingly, which is to search for content. And you can search for content, as we've mentioned, using an if condition. So if a column contains certain data, then perform an action. The notion behind awk is that it's pattern action based. So you supply a pattern, and then it performs an action if the pattern is matched. Now, some other uses of awk from a systems administrative perspective is to be able to extract certain fields from dumps, whether it's var log messages or, let's say, from the PS dump, when you dump or enumerate the processes that are running. For example, let's PSEF. PSEF dumps all of the various processes that are running and the connected users and TTYs and so on, if they're connected to TTYs. As we've discussed earlier, this is pseudoterminal 1 for us. We see other types of pseudoterminals through 8 open. Now, what if we wanted to extract certain fields from the PS dump? Now, PS supports field alterations. We can specify which fields are of interest to us. But what if you didn't remember the syntax for PS and just wanted to rely upon awk to extract the fields from a comprehensive PS execution? That's quite possible as well. For example, we know that when PS executes with EF, it returns these various columns: username, PID, so on, the calling, the parent PID, etc. So supposing we wanted, let's say, the usernames that are running on the system, and then perhaps sorting them to unique or otherwise. So PSEF, pipe the output into awk, and then that's the pattern that will be processed. Now, we're going to have to perform an action. Let's print the first column from the input that's been piped in from PS. And there you see the first column. You could even pipe it to less to look at it, which has a header view ID. And of course, it's redundant, so we can always pipe to another little utility that we've yet to discuss, unique, which will sort the values uniquely and present them to us. So this is one way to look at your output. Now, supposing we wanted other combinations. Let's look at PS to see what combinations might be of interest. Username, PID, and perhaps the final column, which includes the process. So we know that the columns are ordered incrementally. So this would be 1, 2, 3, 4, 5, 6 for the for the terminal field, 7 for the time, and 8 for the process. So we may want 1, 2, and 8, for example. So PSEF grep and show me 1, 2, 8. So now the output's altered appropriately. And of course, to add some delimiter eye candy, we could include something such as the following between each of, and then be sure to include a comma between the fields so that awk parses it appropriately. And in between each we'll put a colon, and this will make things a little bit clearer. So now we've got 1, 2, and 8, and we can reorder the columns. So PS in conjunction with awk makes that possible because awk processes fields. That's what it excels at. So that's one way you may run it. You may also want to, let's say, test your log files for specific dates and then extract various content from them. So for example, if a log file contains certain values in a specific column, that might be of interest. For example, let's awk and we'll do an if. We're not sure which column yet, but if a certain column is equal to a certain value, then let's print perhaps some of the records, which we'll find out momentarily. And that's going to happen from var log messages. So it's still variable, so let's take a look at var log messages to see what may be of interest to us. So let's cat the contents, var log messages. It's always our default file. Now this file contains only 2 entries, so let's go with the other messages file, which contains many more entries. So var log messages, this one contains entries through the 9th. So supposing where column 2 is equal to 9, get us perhaps columns 3, 4, and maybe 5 and 6, or 3 through 6. So let's look at that again, where column 2 is equal to 9. Remember, white space is the separator. So where column 2, so if column 2 is equal to 9, then we know we have items from January 9th for this particular log file, since it contains only items from January. And then we want to print, let's go with columns 3, 4, and 5, or 3, 4, 5, and 6, so 3 through 6. So that should suffice. Now we can just do it this way if we'd like. It's simple. 5 and 6 from var log messages. So again, this combines grepping for specific date into the capabilities of awk, obviating the need for awk. And this is going to be from the messages, the other file. And let's just double check that. That's going to be if, and we must be missing a curly brace somewhere, otherwise it would have worked. Let's just double check our output, single quotes. And this single quote should be outside, and that's more like it. And we'll update our notes. So again, wherever January 9th is found in column 2, or 9 is found in column 2, then extract columns 3 through 6. And of course, we could preserve the original column. So let's go ahead and indicate 1, 2. And let's double check that. Unexpected new line at 6. There must be some sort of error in the input. Let's drop the dump, and it's the same single quotes. So it's actually not the other item. Let's just clean this up. We keep interspersing single quotes, and that's more like it, January 9th. Now we could perform a match if 1 is equal to Jan and 2 is equal to 9, then perform. So of course we could logical AND it as well. We could also print a range of variables if we'd like. Now let's update our output before we clobber things even further. This should be curly brace on the right, on the left, and single quotes on the outside. So let's just note that this prints columns 3 through 6, where column 2 is equal to the number 9. So another way in which you may execute awk. Now, for production purposes, you'll often use grep with awk and with other tools like sed, but grep and awk are often used together to parse large documents like varlog messages to extract content. Sometimes, for example, you may log all of your items to one file and simply want to parse out items for a specific day or date range. So using character classes, for example, you could look for, let's say, 9 through 11 or 3 through 9. Extract those contents, use output redirection to a file, and then have all of those items in a file waiting for you. So for example, if column number 2 is equal to a character class of 9 or 8, then print. So let's set this to a character class of, let's say, 8, 9, which means if it's 8 or 9, then we're interested in it, and then terminate this with a single quote, and then pipe the output to less so that we can see the first item. So now notice that it's received items from the 8th all the way through the 9th. So that's a way you could split the items out and then use output redirection to put the items into, let's say, a log file. So messages, perhaps 2011, 01, 08 through 09. And now, when we look at the contents of messages 2011, 08, it contains items 8 and 9. Of course, it doesn't include the leading month, so we could update this to print column 1 as well through 6. So 1 through 6. And now let's reless, and there it includes records from the 8th to the 9th. So after your log files have been processed or stored, then you can post-process using grep and awk, or awk. In fact, awk can replace grep in most cases if you know the syntax. Grep has a simpler syntax, but awk can do everything that grep can do. Grep cannot do everything that awk can do. Again, for more information on awk, look into Linux CBT awk set edition, where we exclusively focus on awk and sed, showing you more of the ways in which you may use this powerful utility. But that's enough of an intro into how to use awk on your system to be somewhat proficient with parsing field columns into tokens.